Okay, so at the previous lecture, we introduced approximate identities in normed algebras, and we gave some concrete examples of approximate identities. In particular, we explicitly constructed approximate identities in the algebra C0 of X, where X is a locally compact Hausdorff space, and in the algebra of compact operators on a Hilbert space. So today, our first goal will be to show that each C-star algebra has an approximate identity. Well, first of all, let's recall the definition. Suppose that A is a normed algebra. And suppose that we have a net E lambda in A. So let's recall that a net is a kind of generalized sequence. So the only difference is that here lambda, big lambda can be arbitrary, directed, partially ordered set. And by the way, the convergence for nets is defined in exactly the same way as for sequences. So E lambda converges to X if for each neighborhood of X, there is an element, say lambda 0 in our indexed set, such that E lambda sits in this neighborhood if lambda is greater than or equal to lambda 0. Okay, so we say that a net E lambda in A is an approximate identity. AI for short. If for each element all the way in our algebra, E lambda converges to A, and E lambda A converges to A. Okay, so we have the following theorem. Every C-star algebra A has an approximate identity. E lambda, such that E lambda satisfies the following conditions. First of all, so let's denote this condition by AI1. So each element of this net sits between 0 and the identity of the unitization way. By the way, which is equivalent to the following. Equivalently, this means that each E lambda is positive, and the norm of E lambda is less than or equal to 1. So at the end of the previous lecture, we proved that, well, not at the end, but at the previous lecture, we proved that if you have a positive element, then this element is less than or equal to 1 in the unitization of the algebra, if and only if the norm of this element is less than or equal to 1. So these two conditions are indeed equivalent. And condition 2, AI2, our approximate identity is monotone. That is, if lambda is less than or equal to mu, then E lambda is less than or equal to E mu. Okay, so let's now prove this result. Well, the idea is to consider the special case where A is a field of complex numbers. So in this case, well, maybe, well, first of all, before we look at the special case, we explicitly define the index set lambda. So lambda will consist of those positive elements in our algebra, E, such that the norm of E is strictly smaller than 1. So, and this will be our directed set. The order relation on lambda is the usual order relation which was introduced at the previous lecture. So this is a partially ordered set. First of all, we have to show that lambda is directed. This is claim 1. In fact, I'm going to show that lambda is isomorphic to the positive cone of A, to the set of all positive elements, as a partially ordered set. And as a corollary, this implies that lambda is directed. Well, of course, the positive cone is directed because if we have two positive elements, say A and B, then each of them is dominated by their sum, which is also positive. Okay, so to show that lambda is isomorphic to the positive cone, we consider the special case where A is the field of complex numbers. So in this case, lambda is just the half interval, 0, 1. And the positive cone is the positive half line. And it's very easy to construct an order-preserving bijection between these sets. So we consider the following function phi. So let me draw the graph of this function. So this is the graph of phi, and explicitly phi is given by the following formula. Phi of t is 1 over 1 minus t minus 1. So the inverse function psi is also given by the explicit formula. So first of all, let me draw a picture. So this is psi. Psi of s is phi inverse of s. And explicitly, this is 1 minus 1 over 1 plus s. Okay, and now to extend this bijection to an arbitrary C-star algebra, we use the functional calculus. So we take an arbitrary element E in lambda and observe that phi of E, which is defined by means of the functional calculus, is indeed a positive element. Simply because phi is a non-negative function. So this is one of the properties of the functional calculus. If we apply a non-negative function to a normal element, then we get a positive element. So this is a positive element. We also have to show that phi is order preserving. Well, indeed, suppose that E1 and E2 are two elements of lambda, and that E1 is less than or equal to E2. And then, of course, 1 minus E1 is greater than or equal to 1 minus E2. And if we now take the inverses of them, we get the opposite inequality. So 1 minus E2 inverse is less than or equal to 1 minus E1 inverse. So this follows from a property of the order relation So at the previous lecture, we proved that if A and B are positive and invertible, and A is less than or equal to B, then B inverse is less than or equal to A inverse. Okay, so we have this inequality, and this inequality readily implies that phi of E1 is less than or equal to phi of E2. So phi is order preserving. Okay, now let's apply psi. First of all, we observe that for each positive element A, the element psi of A indeed sits in lambda. That is, the norm of psi of A is, so what is lambda? Lambda is the set of those positive elements whose norm is less than or equal to 1. And the norm of psi of A is indeed less than or equal to 1 by the spectral mapping property. So look at this picture. So the spectrum of psi of A is contained in this half interval. So the spectral radius is strictly smaller than 1. And since the element is self-adjoint, well, that's it. So the spectral radius is less than or equal to 1. And since the element is self-adjoint, the norm is also, the spectral radius is strictly smaller than 1. And so the norm is also strictly smaller than 1. So this holds by the spectral mapping property. Okay, now essentially the same argument as above shows that psi is order preserving. If A1 is less than or equal to A2, then psi of A1 is less than or equal to psi of A2. This is a simple exercise. Well, essentially the same argument as above shows that psi is order preserving. So we have two maps now, phi and psi. Phi acts from lambda to the positive cone. Psi acts in the opposite direction. And now the superposition property shows that they are inverse to each other. So the superposition of phi and psi as functions is so if we take their superposition in arbitrary order, we get the identity map. And now the superposition property of the functional calculus shows that well, psi of phi of A is A, and the other way around. Okay, so this completes the proof of claim 1. So we have shown that lambda and the positive cone are order isomorphic. And so since the positive cone is directed, this implies that lambda is also directed. Okay. Well, now we can easily construct our net. Namely, our net will be just the identity map, the inclusion map of lambda into A. So the inclusion map of lambda into A is a net in A, which satisfies the above conditions AI1 and AI2 simply by construction. So this is a net satisfying AI1 and AI2. So now we have to show that this net is indeed an approximate identity. Well, claim 2. I claim that for each positive element in A, such that the norm of A is less than or equal to 1, we have the following. A multiplied by 1 minus E and multiplied by A goes to 0. Over lambda. To prove the claim, we consider the function little t, which already appeared in our construction of functional calculus. So this is just the inclusion map of the interval 0, 1 into the complex plane. And let's observe that t multiplied by 1 minus t to the power 1 over n goes to 0 in the algebra of continuous functions on the interval 0, 1. Well, this is an elementary exercise in calculus. Well, if we now apply the functional calculus, so we now apply this to our element A, and we conclude that A multiplied by 1 minus A to the power 1 over n goes to 0 in A. So we see that if we now take an arbitrary positive epsilon, then we can always find a natural number n such that the norm of this element is less than epsilon. Okay, and now we take an arbitrary element E in lambda such that E is greater than or equal to A to the power 1 over n. And we do the following. So first of all, 1 minus E is less than or equal to 1 minus A to the power 1 over n. Oh, this is clear. Next, we have the same inequality if we multiply by A on the left and on the right. So let's recall why it is so. So this is a special case of the following property. So at the previous lecture, we proved that if A is less than or equal to B, then x star A x is less than or equal to x star bx for an arbitrary element x. So, and here we let x equal A. A is self-adjoint, and so we have this inequality. Okay, and finally, let's recall that the order relation is compatible with the norm. So if A less than or equal to B, A is positive and A is less than or equal to B, then the norm of A is less than or equal to the norm of B. So we can take the norm here. And we get the same inequality. But now the right-hand side is less than epsilon. And that's it. So it shows that if E is big enough, in the sense that E is greater than or equal to A to the power 1 over n, then the norm of this element is less than epsilon. And this means exactly that this net converges to 0. Okay, so this completes the proof of claim 2. And actually, this is almost the end of the proof of our theorem. Now, claim 3. I claim that our net is an approximate identity. Is an approximate identity in A. To prove the claim, we do the following. First of all, we observe that for each E in lambda, we have the following inequality. 1 minus E squared is less than or equal to 1 minus E. This already follows from the first Gelfand-Naimark theorem. So 1 minus E is a positive element, and if we consider the C-star subalgebra generated by this element, then this is the algebra of continuous functions on the spectrum, and for positive continuous functions between 0 and 1, this inequality is trivial. Okay, good. And if we now take an arbitrary positive element in our algebra, such that the norm of A is less than or equal to 1. So let's do the following simple calculation. A minus EA. So what is this? This is 1 minus E multiplied by A. Well, next we use the C-star identity. So the square of the norm of this element equals the norm of A times 1 minus E squared times A. So this follows from the C-star identity. If we now apply this inequality, so this inequality is preserved after we multiply it by A on the left and on the right, as before, and after we take the norm. So the norm of this element is less than or equal to the norm of A1 minus E A, and this goes to 0 by the previous claim. This was proved in claim 2. Okay, so this holds for each positive element whose norm is less than or equal to 1. But by linearity, we conclude that the same holds for an arbitrary element in our algebra. Simply by linearity. First of all, we can obviously replace a positive element in the unit ball by an arbitrary positive element. And then we recall that an arbitrary element in our algebra is a linear combination of 4 positive elements. Okay, so A minus EA goes to 0. Also have to show that A minus AE goes to 0. To complete the proof, we must show that A minus AE goes to 0. But this is, so what is this? This is A star minus EA star star. So this seems to be correct, but the involution is isometric, and since the expression in brackets goes to 0, we conclude that this also goes to 0. Okay, so this completes the proof of claim 3, and this completes the proof of our theorem. So we have constructed an approximate identity. By the way, of course, this proof gives us some kind of universal approximate identity which exists in any C-star algebra. But in some special cases, we can construct a more optimal approximate identity. So here's a useful exercise. If A is a separable C-star algebra, then A has a sequential approximate identity. That is an approximate identity, which is a sequence. Okay. Okay, from now on, it will be convenient to adopt the following convention. When we speak about approximate identities in C-star algebras, we will always assume that our approximate identities satisfy the above conditions AI1 and AI2. So an approximate identity will mean an approximate identity satisfying conditions AI1 and AI2. So AI1 means that the elements of our net are between 0 and 1, between 0 and the identity of the unitization. And we will also assume that our approximate identities are monotone. Okay, good. So our next goal now is to discuss quotient C-star algebras. Okay, so we start with a couple of simple observations. First of all, we have already observed some time ago that if A is a Banach algebra and I is a closed two-sided ideal, of A, then the quotient of A modulo I is also a Banach algebra. And norm on this algebra is the usual quotient norm given by the following formula. And it's very easy to observe that if now A is a Banach star algebra, and I is a closed two-sided star ideal, then the quotient of A module I is a Banach star algebra. So the norm is given by the above formula, and the involution is also quite obvious. So this is very easy. And now the natural question is, what if A is a C-star algebra? Can we claim that the quotient of A module I is also a C-star algebra? The answer is yes, but quite surprisingly, the proof of this fact is not entirely trivial. And the proof will be based on approximate identities. So first of all, we need the following lemma. Suppose that A is a C-star algebra, and suppose that I is a closed left ideal. Closed left ideal array. I claim that I has a right approximate identity. A right approximate identity E lambda, satisfying conditions AI1 and AI2. So what is a right approximate identity? The definition is more or less obvious. This means that this approximate identity is a net E lambda such that A E lambda goes to A. So in the definition of the approximate identity, we had two conditions: A E lambda goes to A, and E lambda A goes to A. So it is two-sided. And here we claim that I has a right approximate identity. To prove this result, we reduce everything to C-star algebras. Namely, we'll let B denote the intersection of I and I star. And it's clear that B is a C-star subalgebra. B is a C-star subalgebra array. Well, indeed, it is a closed subalgebra because it is the intersection of two closed subalgebras, I and I star. And it is a star subalgebra because it is the intersection of I and I star. So it's stable under involution. So it is a C-star subalgebra. And by the previous theorem, we can find an approximate identity in this subalgebra. So now let E lambda be an approximate identity. In B, satisfying AI1 and AI2. I don't write this because this is our standard convention. When we speak of approximate identities in C-star algebras, we always mean approximate identities satisfying AI1 and AI2. Okay, I claim that this approximate identity is exactly what we're looking for. Well, indeed, if we take now an arbitrary element A in I, so let's calculate the norm of A minus A E lambda. So we write this element as A multiplied by 1 minus E lambda. And we apply the C-star identity. So the square of the norm of this element is equal to the norm of 1 minus E lambda A star A 1 minus E lambda. So this follows from the C-star identity. Now the norm of the first element here, namely of 1 minus E lambda, is less than or equal to 1. So we can estimate this as follows: A star A multiplied by 1 minus E lambda. And now we observe that this element A star A sits in B. Because it sits in I is a left ideal, and it is self-adjoint. So it is a self-adjoint element in I, and so it sits in B. And that's it. So this is an element of B, and lambda is an approximate identity of B. So this goes to 0. And this completes the proof. We have shown that E lambda is a right approximate identity in our ideal I. Okay. We can now discuss the quotients of C-star algebras. So we have the following theorem. Suppose that A is a C-star algebra and I is a closed two-sided ideal. Then I claim that, first of all, I is a star ideal. So each closed two-sided ideal of C-star algebra is a star ideal. Second, suppose that we have an approximate identity. Suppose that E lambda is an approximate identity in I. Then, for each element A in our algebra, the norm of the respective element in the quotient A plus I can be given by the following formula. Well, this is limit of A minus A E lambda. Or instead of the limit, we can take the infimum, and the result will be the same. And finally, part 3, I claim that the quotient of A modulo I is a C-star algebra with respect to the quotient norm. Okay, so let's now prove this result. To prove part 1, we use our lemma. So I is a closed two-sided ideal. In particular, it is a left ideal. So it has a right approximate identity. So let E lambda be a right approximate identity in I, satisfying conditions AI1 and AI2. Well, so we want to show that I is a star ideal. We take an arbitrary element A in I, and we do the following. So we know that A minus well, we know that A E lambda goes to A. So when we apply the involution, we see that E lambda A star goes to A star. But now E lambda A star sits in I, because I is also a right ideal. I is also a right ideal. E lambda sits in I. So E lambda A star is in I again, but I is closed. I is closed, so this implies that A star sits in I. And that's it. So this shows that I is a star ideal. Okay. Now let's prove the second part. So we take an approximate identity in I again, and we have to to prove the following formula. To prove the formula, we take an arbitrary element B in our ideal. We take an element A in our algebra, an element B in our ideal. And we observe that A minus AE lambda can be, so first of all, this is A multiplied by 1 minus E lambda. And we can evaluate this as follows. This is less than or equal to A plus B times 1 minus E lambda plus B multiplied by 1 minus E lambda. This is just the triangle inequality. Just the triangle inequality. Now the first summoned is less than or equal to the norm of A plus B, because E lambda is between 0 and the identity. And the second summoned, we keep it the same. So this is B minus B E lambda. Okay. But now, since B is an element in our ideal, we see that this element goes to 0. And now, if we now take the infimum over B, we see that the infimum of this expression over B is just the norm of A in the quotient. So this inequality implies that the upper limit of A minus AE lambda is less than or equal to the norm of A plus I in the quotient. Okay, but on the other hand, it's clear that the norm of A plus I is less than or equal to the infimum over lambda of A minus AE lambda. That's clear because AE lambda sits in our ideal I. And this is less than or equal to the lower limit of A minus AE lambda. So we get the following chain of inequalities. And this chain implies that the upper limit is less than or equal to the lower limit. And this means that the limits, these two limits are the same, and the limit exists and is equal to the infimum. So this implies our formula 2. So this norm in the quotient is equal to the limit and is equal to the infimum. Okay, and now we apply this formula to showing that the quotient is a C-star algebra. So this is part 3 of our result. Okay, so we take an arbitrary element A in our algebra, and we look at A plus I squared. By formula 2, this is the infimum over lambda of A times 1 minus E lambda squared. Now we apply the C-star identity. So this is the infimum over lambda of, well, maybe I do it in the next line. So this is the infimum over lambda of 1 minus E lambda A star A 1 minus E lambda. Now the first element here, 1 minus E lambda, is between 0 and 1. So this is less than or equal to the infimum over lambda of A star A multiplied by 1 minus E lambda. And again, by formula 2, this is nothing but the norm of A star A in the quotient. And that's it. So we have shown that in our algebra, in our quotient of A modulo I, the norm of A squared is less than or equal to the norm of A star A. And we have already observed that this inequality is actually equivalent to the C-star axiom. So the quotient is a C-star algebra. Okay, so this completes the proof. Let's now look at two concrete examples of quotient C-star algebras. By the way, both examples I'm going to show play an important role in the extension theory of C-star algebras and in K-theory. The first example, example 1, is the so-called Kalkin algebra. So suppose that H is a Hilbert space, and let Q of H, script Q of H, denote the quotient of B of H, of the algebra of bounded operators on H, modulo the ideal of compact operators. Well, we know that the compact operators form a closed two-sided star ideal in B of H, so the quotient is a C-star algebra. And this algebra is called the Kalkin algebra of H. I'd like to stress that there seems to be no obvious way of proving that the Kalkin algebra is a C-star algebra unless we use the approximate identities. Okay, and one more example, example 2, is the Toeplitz algebra. So suppose that H is an infinite dimensional separable Hilbert space. Say the little space. And we choose a countable orthonormal basis, En, an orthonormal basis of H, and we'll look at the respective right shift operator. So the right shift operator is a bounded operator on H, uniquely determined by the following formula. So it takes En to En plus 1 for each n. This is the right shift operator. Clearly, it is an isometry on H. Now, by definition, the tuplets algebra. The tuplets algebra is the C-star subalgebra of P of H, that's denoted by script T. The C-star subalgebra of V of H generated by this right shift operator, generated by S. So in other words, this is the smallest C-star subalgebra of BOH containing the right shift operator. More explicitly, this algebra can be described as follows. And so this is the closure of the linear span of all elements of the form, of all monomials of the form s to the power k, s star to the power l, where k and l are non-negative integers. This equality readily follows from the fact that S is an isometry. So in other words, S star S is the identity map. So this equality easily implies that the linear span of all such monomials is indeed a star subalgebra, where we multiply two such monomials to get a monomial of the same form. So this linear span is indeed a star subalgebra, and clearly this is the smallest star subalgebra containing S. So when we take closure of the linear span, we get precisely the C star subalgebra generated by S. So this is the tuplets algebra. So now useful exercise. First of all, I claim that the ideal of compact operators is contained in the tuplets algebra. So a hint to this exercise is to look at the operator 1 minus SS star, which is compact. Okay, exercise 2. So what if we take a quotient module of this ideal? Well, by our previous result, this will be a C-star algebra. I claim that this algebra is isometrically star isomorphic to the algebra of continuous functions on the circle. So here T is the unit circle on the complex plane. Here the hint is as follows. First of all, this quotient is the first step is to show that the quotient is commutative, because it is also generated by S. Of course, S and S star don't commute, but they commute modulo the ideal of compact operators. So this implies that the quotient is commutative. So it is a commutative unital C-star algebra. So it is isomorphic to the algebra of continuous functions on its maximal spectrum. But since it is singly generated, its maximal spectrum is homomorphic to the spectrum of the generator, that is, of the element S considered as element of the quotient. And this spectrum can be calculated explicitly. So it follows from the classical Fredholm theory, from the theory of Fredholm operators, that the spectrum of an element in this quotient is the essential spectrum of the respective operator. And it's a simple exercise in functional analysis to show that the essential spectrum of S is the unit circle. So the quotient is isomorphic to the algebra of continuous functions on the circle. And so we get the following exact sequence of C-star algebras, which is called the tuplets extension. tuplets extension. This is the following exact sequence of C-star algebras: K of H, T, and the algebra of continuous functions on the circle. So this is just the inclusion map, and this is the projection P, which follows, which is a composition of the quotient map with the isomorphism from the previous line. So I claim, and this is exercise 3, that the tuplet extension doesn't split. Which means that there is no star algebra homomorphism J from C of T to the tuplets algebra, which is a section for P, such that Pj is the identity map. So the tuplets algebra, and especially the tuplet extension, are very important ingredients in K-theory of C-star algebras. And in particular, they play an important role in the proof of the Bott periodicity for K-theory of C-star algebras, which was suggested by Joachim Kuntz. Okay. Okay, so that's all I wanted to tell you about quotients. Now our next goal is to discuss positive functionals on C-star algebras. From our point of view, positive functionals will be important because they will enable us to construct representations of C-star algebras. So we start with the following pure algebraic definition. Suppose that A is a star algebra and F is a linear functional on A. We say that F is positive and write the following symbol. If F of A star A is greater than or equal to 0 for each element in our algebra. And one more definition. If A is a Banach star algebra, then if we have a bounded linear functional F on A, we say that F is a state if it is positive and the norm of F equals 1. The norm of F is exactly 1. In Russian, state is состояние. The terminology here comes from physics. Well, maybe I'll tell you more about this a bit later. Let's now look. Now, first of all, let's observe the following. So this definition works for an arbitrary star algebra. But let's observe that if A is a C-star algebra, if A is a C-star algebra, then a linear functional f on A is positive, if and only if it takes positive elements, two non-negative numbers. This is immediate from our earlier characterization of positive elements. So let's recall that an element of a C-star algebra is positive, if and only it can be written in the following form: A star A for some element of the same algebra. Okay, let's now look at some examples of positive functionals. Example 1. First of all, it's clear that each star character is positive. This is clear from the definition, because if we apply it to A star A, then we get the absolute value of A squared, which is non-negative. So in particular, if A is a C-star algebra, if A is a C-star algebra, and chi is a non-zero character, then chi is a state. Because the norm of a non-zero character is exactly 1. Okay. One more example, which is purely commutative. Example 2. Let A be the algebra C0x, where X is a locally compact Hausdorff topological space. So we take an arbitrary finite positive Radon measure. Say mu, a finite positive Radon measure mu on X, and we define a functional f mu on our algebra to be the integral over with respect to mu. So this is well defined because mu is finite. And clearly this is a positive functional. If A is non-negative, then the integral is also non-negative. Also, it is bounded, and its norm is nothing but mu of X. This is a simple exercise. So we see that f mu is a state even only if mu is a probability measure. Mu of X equals 1. In fact, this example describes all positive functionals on C0 of X. This really follows from the Riesz representation theorem. This theorem implies in particular that the above correspondence is a bijection between the set of all finite positive random measures on X and the set of all positive linear functionals on C0 of X. So this correspondence takes each measure mu to the respective integral f mu. So from this point of view, positive functionals on C-star algebras can be interpreted as non-commutative analogs of finite positive Radon measures. Okay, let's now look at something non-commutative. Example 3. Probably the simplest example of a non-commutative C-star algebra is the algebra of square n by n matrices. So let A be the algebra of square n by n complex matrices, or, which is the same, the algebra of bounded operators on a finite dimensional Hilbert space. First of all, we have the following canonical example of a state, the so-called normalized trace. We define a functional f on A by the following formula. It's the so-called normalized trace. So this is an example and exercise at the same time. I claim that f is a state. This is very easy. In fact, it's also very easy to describe all states on this algebra. First of all, for each linear functional f on this algebra, there exists a unique operator, a unique element S of the same algebra A, such that f is given by the following formula. This is the trace of the product. So we denote this functional by fs. Next, I claim that this functional fs is positive, even only if the respective operator s is positive. And finally, fs is a state even only if s is positive and the trace of s is 1. So example 1 is a special case of this construction, which corresponds to the identity operator divided by n. Okay, example 4. Let's now look at something infinite dimensional. Let now A be the algebra of bounded linear operators on an arbitrary Hilbert space, H. We take an arbitrary vector, xi in H. And we define a linear functional f xi in our algebra by the following formula. F xi of t is the inner product of t xi and xi. It's clear that f xi is linear, and it is positive because if we apply it to t star t, so the result will be the inner product of t xi by itself, which is non-negative. So this implies that f xi is a positive functional on B of H. It's also more or less clear that the norm of this functional is the norm of xi squared. So the inequality follows from the Cauchy-Bonnikovsky-Schwarz inequality, and if we substitute the identity operator, we see that this is the equality. So in particular, we see that f xi is a state if and only if the norm of xi is 1. States of this form are called vector states. So this is a state on B of H given by a unit vector in our space. Well, let me also say a few words about where the terminology comes from. In mechanics, there are two fundamental notions, states and observables. For example, in the mathematical model of the classical mechanics, states are the points of a smooth manifold, which is called the phase space of our system. And the observables are functions on this manifold. The mathematical model of the quantum mechanics is different. Now, the states are vectors on a unit sphere of a Hilbert space, and the observables are self-adjoint operators, usually unbounded self-adjoint operators on the space. And if T is such an operator, an observable, then this number, the inner product of T xi and xi, is interpreted as the mean value of T in the state xi. States of this form are sometimes called pure states. There are also so-called mixed states, which are defined similarly to example 3. But now, since our space H is infinite dimensional, in order to make sense of this expression, take the trace of the product, we must assume that S is not just an arbitrary operator, but S is a so-called trace operator or a nuclear operator on H. Okay, maybe one more example of state. Example 5. Let A be the group L1 algebra of a discrete group G. Also, this is an example and an exercise at the same time. First of all, consider the following functional on A, which takes each element little a to little a evaluated IV identity. So I claim that this is a state. Second, let's recall that the algebra little one. Of course, it's not a sister algebra, but it can be embedded into bigger algebra, which is now a sister algebra, the so-called the reduced sister algebra of G. So we take the left regular representation of little l1 on the little l2 space, and the closure of the image of this representation is the reduced sister algebra of G. So I claim that F extends to a state on the reduced sister algebra. Let's denote the state by F tilde. And finally, I claim that F tilde is a vector state. Okay. So our final result for today will be the following theorem, which shows in particular that all positive functionals on a sister algebra are automatically bounded or are automatically continuous. So suppose that A is a sister algebra, and suppose that F is a positive linear functional on A. Then, first of all, F takes self-adjoint elements of A to real numbers. Second, I claim that F is compatible with the involution. It takes A star to the complex conjugate of F of A. And finally, I claim that F is continuous. Okay, so to prove this result, first of all, we recall that each self-adjoint element is a difference of two positive elements, A plus minus A minus, where A plus and A minus are positive elements. And this completes the proof of part one, because F takes A plus F and A minus to non-negative numbers. Part two easily follows from part one. Actually, we can apply the same argument that we used when we proved that every character of a sister algebra is a star character. Here, the proof is identical to the case of characters. So basically, we take A, we represented A in the form B plus IC, where B and C are self-adjoint. And since A star is B minus IC and F of B and F of C are real, this implies that F of A star equals the complex conjugate of F of A. Okay, finally, let's show that F is continuous. To prove that F is continuous, first of all, we show that F is bounded on positive elements. So I claim that there exists a non-negative constant C such that f of a is less than or equal to c times the norm of a for each positive element a. Well, assume that this is not the case. And if this is not the case, then for each natural number n, we can find a positive element an, such that the norm of an is less than or equal to 1, and such that f of an is greater than or equal to 4 to the power n. And let's now look at the following element. Let little a be the sum of a to the power n, of an divided by 2 to the power n. Well, f is positive. Well, first of all, this series converges because an is in the unit ball. Now, since our functional f is positive, it is monotone. So a is greater than or equal to each of the sums. So this implies that f of a is greater than or equal to f applied to an over 2 to the power n. But by assumption, this is bigger than 2 to the power n for each n. And obviously, this is a contradiction because f of a doesn't depend on n. So this contradiction implies that such a constant c exists. So for each positive element, we have this inequality. And to complete the proof, we must show that f is bounded everywhere on A. So we take an arbitrary element in our algebra, and we decompose it in the following form: b plus minus b minus plus I, c plus minus c minus, where b and c are self-adjoint. And c plus and b plus and b minus, c plus and c minus are the same elements which were discussed at the previous lecture. So their difference is b and their product is 0. Okay, and now we recall that the norm of b plus and the norm of b minus is less than or equal to the norm of b. This follows from the explicit construction of these elements. And the norm of b is less than or equal to the norm of a, simply because b is a plus a star over 2. And similarly, the norm of c plus and the norm of c minus is less than or equal to the norm of a. So if we now apply f to a, we see that f of a, well, the absolute value of f of a is less than or equal to 4c times the norm of a. So we simply estimate each summand, f of b plus, f of b minus, and so on. So each of them is less than or equal to c times the norm of a. So as a result, we get this inequality. And that's it. So this inequality implies that f is bounded or equivalently continuous. By the way, an interesting exercise, which is not trivial, but interesting, is to show that the same result holds for each Banach star algebra with a bounded approximate identity. But on the other hand, this result fails for arbitrary Banach star algebras. Okay, so so that's all for today. At the next lecture, we continue our discussion of positive functionals. We discuss a useful criterion of positivity for functionals on a sister algebra. We prove the extension theorem for positive functionals, which will enable us to extend positive functionals from a subalgebra to a bigger algebra. And then we discuss how to use positive functionals for constructing representations of C-star algebras. Okay, thank you.